gases. Alright, so this chapter is all about gases and how do we measure them, especially things like volume, temperature, and pressure of the gas. And then we'll look at from a molecular point of view what changes those, what causes them to change, that kind of thing. Alright, so let's start first off talk about pressure. Pressure is defined by force per area. How much in a given area, how much force are you putting on that? And so if you think of the inside of a balloon perhaps, and you're blowing it up, and there's gas, of course, the inside of it. On the inside surface, there's the gas that's pushing on it. That's what pushes it out, right? And of course, on the outside of the balloon, the atmospheric pressure is pushing on it. And when those two are equal, then of course the balloon isn't getting larger or smaller, it's just staying put. Alright, so we've got this idea of how much force do you put in per square area. Force per area is what's pressure. Alright? If you think about our atmosphere, we've got all of this gas above us going up and up and up. And if you take a 1 inch kind of a column, so you've got 1 inch on the ground, you think of it going up, 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 up forever and ever, all the way up through the atmosphere. You've got all that gas because of gravity that's pushing down onto that 1 square inch. It's pushing down because of the weight of that gas. How much would that gas weigh? On planet Earth anyway, with our atmosphere, how much is up there with our gravity? Turns out to be 14.7 pounds. 14.7 pounds if you weighed all of that going all the way up top, which is not small, right? That's substantial. It's like a bowling ball pressing down every square inch. That's how much that gas weighs. Again, we're used to it, but if we put an additional bowling ball on top of that, well, we wouldn't be used to that, and we definitely feel it. Like, wow, what's all this stuff pushing down on me? All right, so 14.7 pounds per square inch. Pounds per square inch. Oh, well, that's what we call PSI. PSI, pounds per square inch. That is pressure of a gas. You know, you go outside and you pump your tires up for your car. Maybe it's 35 PSIs is what you pump it up to. That's the pressure inside that tire then. That many pounds per square inch. All right, so PSI, there's our first unit of pressure. All right. Other units of pressure, lots of them. Lots and lots of them. I guess we got just so many units of pressure that have been used and are still used, and we need to be familiar with at least the main ones. So the book has a large table, and I've summarized the most important ones here in my notes. The first one, what are the actual SI metric units, the official ones for pressure? Well, that's a Pascal, PA right there, Pascal. A Pascal in it's a derived unit, and in terms of its base units, that'd be a Newton per meter squared. Well, that's because it's force per area. The unit of force is a Newton, and a Newton is a kilogram meter per second squared. And so if you take it all the way down, and I didn't do that here, but a Newton meaning a kilogram meter per second squared, and you do that whole thing per meter squared, then that's the actual base units of pressure. All right. Of course, we don't go around saying that, oh yeah, I've got so much pressure and it's so many kilogram meters per second squared per meter squared. No, we just say Pascal or something like that. But do notice that if I want to convert things from base units into a Pascal, the units I'd have to use would be a meter and a second and a kilogram. Right? So not a gram, but a kilogram actually. Right? And for volume, it wouldn't be a liter, it'd be a cubic meter. And so that's a small point. We're going to have to come back to that and make sure we follow that rule. But right now, just know, hey, a Pascal, that's a unit of pressure in the metric system. PSI, that's what we already talked about before, pounds per square inch. And once in a while, we do have to, I guess, use that value, or that unit. Not very often. Like I said, pumping up your car tires, perhaps, something like that. But PSIs are not used a whole lot. But we can convert if we're given pascals, we could easily convert that over. All right, a pound per square inch. Of course, I'd have to convert inches to meters and pounds to newtons. But yeah, I could do that, and then I'd have it converted over to a Pascal. Right. 14.7 is, again, the weight of that gas of an atmosphere. So 14.7 PSIs are what we call 1 atmosphere. 1 atmosphere of pressure. And we're going to see in just a second here, well, that's the next line, ATMs, atmosphere, is a third unit of pressure that we will use. And that one's used quite a bit, actually. So let's go down to that. 1 atmosphere of pressure is called an ATM. Now, of course, if you go high on a mountain, If you go down to sea level, if you're talking about a rainy day or a sunshiny day, that pressure does change. We know that we get high pressure systems and low pressure systems, right? And so an ATM, one ATM is kind of the average across the whole Earth at sea level. What's that average pressure of the atmosphere? We call that, whatever it is, one ATM, one atmosphere. All right, so what does that equal in PSIs? 14.7, we already mentioned that. What does it equal in pascals? Turns out to equal 101,325 pascals. 101,325. So obviously a pascal must be a pretty tiny unit. It's kind of like measuring the distance from here to town, from town to town, I should say, in millimeters, something like that. You could do it, but it's a small unit to use, and a pascal is a pretty small unit. But again, you're going to see it a lot because it is the official unit. All right, but 101,325 pascals is in 1 atmosphere. And I can interconvert then between atmospheres, pascals, PSIs. I've got these conversions. Another commonly and more often, year by year, more and more oftenly used is a bar. That comes from the same word like barometric, meaning atmospheric, barometric pressure. That's how we measure that of the atmosphere. So a bar, a BAR, that is defined as 100,000 pascals. Why do we need that? And why is it being used more and more often? Well, a bar being 100,000 pascals is very, very close to an average atmospheric pressure, which is 101,000. Right? Very, very close, just a hair off. And so, more and more often, you'll see that, yeah, okay, 1 atmosphere is the actual average, but pretty close to 1 bar, and so people are starting to use that instead. And it's easy to convert, right? 100,000 pascals. And a pascal is the official SI unit, and so 1 bar fits nicely with that, being a multiple of 10 of a pascal. Another very commonly one used is millimeters of mercury. And that's because some of the first measurements were done by measuring a column of mercury and how much force it put down. We're going to do some problems on that. So literally a millimeter of mercury is a unit of pressure. Now that sounds strange because it's a distance, and we'll see why it makes perfect sense in just a second. So millimeters of mercury, that's the same thing as a torr, just a different name for exactly the same unit, a torr, named after the scientist. So how does that convert? Well, 760 millimeters is what 1 atmosphere is. And so if I measure the pressure, the average pressure of an atmosphere, it turns out to be 760 millimeters. Or if I want to use the bar as the average for an atmosphere, well, then that's 750 millimeters. Well, like we said, an atmosphere and a bar are very close. But here are the conversions again. So a bar, 100,000 pascals, 760 millimeters, the same thing as an atmosphere, or 750 millimeters, the same thing as a bar. One last one, inches of mercury. Well, if I could do it in millimeters, I could do it in inches or meters or really anything. Inches of mercury, perfectly good unit of pressure as well. It's used in aviation all the time. If you go in and get your pilot's license and you want to fly, most atmospheric pressures for planes are measured actually in inches of mercury. And the airport will tell you, today's pressure is so many inches of mercury. Turns out that 29.92 inches of mercury is 1 atmosphere on average. Or if you want to convert that to pascals, 1 inch of mercury is 3,386 pascals. All right, so lots and lots of different units of pressure, and you'll need to be able to interconvert between them. The ones that are most commonly used, probably are pascals, atmospheres, bars, and millimeters of mercury, those 4. Example 9.1, let's go to that in the textbook here. It says the United States National Weather Service reports pressure in both inches of mercury and in millibars. Convert the pressure of 90 or 29.2 inches of mercury into these various units. All right, so unit conversion, just like we've done in other chapters, except now we got units of pressure. So first of all, into torr. What is that? All right, well, we're starting with 29.2 inches of mercury. And remember, an inch of mercury is that distance of mercury, if you will, inches. When they want it to go, instead of from inches, they want it to go to millimeters. Why do I say that? Because they asked for torr. And if you remember, torr is just another name for millimeters of mercury. Alright, so all I really got to do is say, alright, instead of inches, I'll put that on the bottom so it cancels. I want millimeters of mercury. Do I know the conversion of that? Yep, because 2.54 centimeters is the same thing as an inch, or in other words, 25.4 millimeters is 1 inch. There we go. That's millimeters of mercury, which is the same thing as a torr. So I can put my equal sign here. Let's go over to the calculator. 29.2 down here, and times 25.4 divided by 1. So the answer is 741.6800. So 3 sig figs gives me 742 torr. All right. Atmospheres is next. What do I do that in atmospheres? Well, again, go back up here. I've got the idea that 29.2 inches of mercury is the same thing as 1 atmosphere. So there's a good conversion right there. I can use 29.2. Let's convert. Whoops, I forgot to put my units. Come on, eraser. There we go. That was supposed to be in inches of mercury. We're going to convert that to atmospheres. So inches of mercury on the bottom, atmospheres on the top. 1 atmosphere is the same thing as 29.92 inches of mercury. That cancels. Back to the calculator. 29.2 times 1 divided by 29.92 equals 0.975935. So again, sig figs here, so that will be 0.976 atmospheres. So just a little bit under 1 average atmosphere. Next, they want to try us to go to kilopascals. Alright, so coming back up here, right now I've got inches of mercury. Oh, 1 inch of mercury here is 3386 pascals, and then I can go to kilopascals from there. Alright, so let's give that a try. 29.92 inches of mercury as usual. Inches of mercury on the bottom, so it cancels. Pascals on the top. 1 inch of mercury is, again, 3386 pascals. So that cancels, and now if I want to go to kilopascals, pascals to kilopascals, there's 1,000 normal little pascals in 1 kilopascal. So that cancels. Alright, back to the calculator. 29.2, I'm going to say times 3386 divided by 1 times 1 and then divided by 1,000 equals 98.87. So 98.9 kilopascals. And finally, millibars. Again, just need that conversion factor. 29.2 inches. What do I know about bars or millibars and inches? Well, let's say I know that 1 bar is 750 millimeters of mercury. So let's do that first. Let's go from inches of mercury to millimeters of mercury. Hey, we did that before. Remember we said there's 25.4 millimeters in 1 inch. And then from millimeters of mercury to bars, millimeters mercury to bar, there are exactly 750 millimeters in 1 bar. Again, that's from those conversions and the tables. And now they want millibars, and so bars to millibar, there's 1,000 millis in a normal of anything like that. So put your equal sign and we can finally do this one. 29.2 times 25.4 divided by 750 and then times 1,000. The answer is 988.90. Alright, so 989 millibars. Alright, so conversions, same way you've done all of them. It's just there's a new set of units here that you're perhaps not used to and just have to get used to that. Okay, atmospheric pressure can be measured with a barometer. That makes sense. A barometer measuring barometric pressure. Again, the unit of a bar, that's all the same. And so the BAR, a barometer. And this is what a typical barometer would look like over here. You've got, as you can see, a long glass tube essentially. And you've got a pool of mercury down here. Actually, it could be any liquid. Here they're showing what it is if you did water. Mercury works well because it's so dense. Okay, you fill this column, turn it upside down, fill it with your liquid, and it's sealed at the bottom there. which you're going to flip over, it becomes the top, right? So you fill it up with mercury, and then put your finger over, turn it over, and put it down in your pool of mercury. I hope you're wearing special gloves because mercury does absorb through the skin and it's toxic. But anyway, this is how you would do it. And that column of mercury, of course, would want to drain down and fall. On top of where it's draining, well, it's sealed off, so there's no air or anything in that. It's just a vacuum. And so we don't have anything else pressing down other than just the column of mercury itself going down. Right? And so it's trying to push down. At the same time, though, it's submerged in this pool down here of mercury, and you have on the outside of the tube, you have the atmospheric pressure pushing on the liquid surface of that mercury. And the neat thing about liquids is that it can deliver that force in any direction, including back up the column. And so, on the one hand, you've got gravity trying to pull that column of mercury down, but then you've got the pressure due to the atmosphere of the air pressing down on the atmosphere, pushing back up on that mercury. And when those two forces are equal, that column will stop dropping. Kind of a neat idea, right? And you can do this for mercury. It goes down and it goes down and it goes down, and it finally stops at about 760 millimeters. That's not too high. 760 millimeters. Yeah, well, 0.76 meters, right? So 3/4 of a meter. If it were a denser liquid than mercury, which would be pretty hard to do. Mercury is one of the most dense liquids out there. Really, really a lot of mass for every volume. But if you had a denser liquid, well, gravity would have a bigger effect and it would drop down further. You wouldn't need as high of a column, that is to say, to balance the atmosphere. If you have a less dense liquid like water, well, you're going to need a much taller column of water to get enough force to balance that atmospheric pressure. And so what your liquid you use, that's important, and then the height of the column is important. So there we go. There's a very simple way to measure the barometric pressure of the atmosphere, just a column of mercury. And you'd literally, right down in the picture here, you'd literally take a measure of the height of that column. So take a ruler, hold it over, hey, and it goes up 760 millimeters. There you go. That's the barometric pressure. So you see, measuring the height, distance of a liquid is a good unit of pressure. All right. How would you actually convert that height to pressure if you don't have, say, mercury? Because we have the idea of millimeters of mercury is the pressure. Well, what if I had millimeters of water or something like that? Well, you'd have to go back to a basic physics formula such as this one, the idea of the force per unit area, per square area. And so pressure would equal the height of the column times the density, the Greek letter rho here, density of the liquid times gravity, the acceleration due to gravity. Right? With the height of the column, you're going to measure the density. Well, depending on what it is, you'd have to know the density of your liquid. And G, well, G is always the same thing. Gravity is 9.81 meters per second squared. And so you just measure that height, plug it in, and you'd get the pressure, actually. In terms of pascals, if you use the right units for these three things that you're pushing in. So let's do an example. 9.2. Let's call that up here. 9.2 says, show the calculation supporting the claim that the atmospheric pressure near sea level corresponds to the pressure exerted by a column of mercury that's about 760 millimeters high. The density of mercury is 13.6 grams per cubic centimeter. All right, so 13.6 grams per cubic centimeter, that's how dense this mercury is. Of course, one atmosphere, we expect it to be 760 millimeters of mercury. We know that conversion. They're saying, prove it. All right, well, in other words, let's solve for H. Let's see if H really does equal 760 millimeters when we plug into our equation. So pressure is the height times the density times gravity. All right, pressure of one atmosphere, let's say here. Or, since we're going to be using meters and the weight of it and the density is grams, we're going to be using SI units. All right? And so instead of an atmosphere, let's use the SI unit. We know it's 101.325 pascals. That's the average atmospheric pressure in pascals, again, from the conversion table. All right, so that's our pressure. It should equal the height, and that's what I'm trying to solve for, times the density. The density is let me go up here, 13.6 grams per cubic centimeter. Now, I don't want grams and I don't want cubic centimeters, so I'm trying to go to the base units of the MKS system, so it'll come out in pascals. I have to go to, remember, kilograms, and I have to go to meters. That's what MKS stands for, meter, kilogram, second. So I need to do a little conversion here. Grams to kilograms, well, that's easy. That's just 1,000. All right, so now I've got kilograms per cubic centimeter. Meters instead of centimeters, and so centimeters on the top, so it'll cancel with that one. Meters on the bottom. There's 100 centimeters in a meter, but these are cubes, so you have to cube the whole thing. Right? That will give me kilograms per cubic meter. That's what I really want. So let's go to the calculator and try that. 13.6. I'm going to divide that by 1,000, and then I'm going to multiply by 100 cubed. 100 raised to the third power. All right, so 13.6 times 10 to the 3. So in other words, 13,600 kilograms per cubic meter. All right, that's just the density, but in the units, the correct base units for the MKS system. That's what I'll put in for density here in my formula. 13,600 kilograms per cubic meter. And next, G. G is, again, 9.81 meters per second squared. Meters, that's okay. And seconds squared, that's okay too. Those are already in the correct MKS units. All right, I think I can solve this for H now. H, turn it around. Again, I have to go to those units which maybe you're not used to, but the Pascal is derived from MKS, these agreed upon set of metrics. And it's not the gram, it's the kilogram. You know, it's not the centimeter, it's the meter. So you've got to go to those if you're going to just blindly use 101,325 pascals. All right, anyway, let's go over here to the calculator and figure this out. 101,325 divided by 13,600 divided by 9.81 equals, hey, look at that, 0.759466. All right, and so three significant figures that would round off to 759, whoops, 0.759. What are the units? MKS here, meters. So 0.759 meters of mercury. That's how high this column is, or 760 millimeters, right? Just multiply by 1,000 to get to that. Well, I shouldn't have rounded off. I'm so used to thinking just 760 that I automatically put it. But this calculation gave me 759. Close enough for me. All right, so 759 millimeters of mercury is what 1 atmospheric pressure should equal. Yep, we have verified and shown that to be true. All right. A manometer is very similar to a barometer, a barometer, or a manometer. Mano, baro, whatever. Right? A manometer measures pressures of other gases. So instead of having my tube right here come down just into a pool of mercury and then the atmospheric pressure pushing down to give me that pressure back, that back pressure, instead this curves around and goes to a gas. And so it's the gas, how much pressure is in there, that's what's giving me that back pressure, that pushback, if you will. You can have both a closed or an open-ended manometer. A closed-ended means that this is sealed off, or an open-ended, it's just a tube and it just goes and it's open to the atmosphere. So in a closed-ended, you've got nothing but a vacuum up here. Over here, it's open, so you've got the atmospheric pressure pushing down into that open end as well. And so you just have to either not include atmospheric pressure, or in the case of a closed, or make sure to include the pressure of the day, the atmospheric pressure, in your measurement. Now, what else is in here? Mercury, usually, as usual. Any liquid could work again, but mercury is best because it's so dense. All right, so you've got this mercury in here. If you had no extra pressure at all, then this would just be level on this U tube here. This U tube, not like the videos, but on this U portion of the tube, the mercury would just kind of come up to the same level. It would be filling it all up. If you had no difference from the left to the right side, they would be even. But then if from one side I start putting pressure on, well, then it's going to take that and it's going to push that side down and that side up. And so I'm going to get this new level where I'm going to get this height that has been pushed. It goes like that. Okay. And the height that it pushes, well, now I've got a column of mercury. I can measure it, millimeters of mercury, and that tells me how much pressure is going on. All right, so look at this first picture again. I've got closed here, vacuum, so there's nothing else pushing here. I've got this gas here that's pushing this down. There's H, and so I think, all right, there's the H that's on my right side of this diagram, pushing downward as I've drawn here, pushing down here, push it against the gas, right? And it's going to go until, again, those forces are equal to each other, and it'll stop moving then and it'll level off. All I got to do is measure the height of that, and it's the same calculation before. The height times the density times the gravity. Of course, if I'm using mercury, it's even easier. Just what is the height? There you go. Millimeters of mercury, there's my pressure. And if I wanted to convert it to something else, I could. So we'll do a problem on that in just a second. Here's an open-ended one. Same exact idea, except because it's open-ended, I also have the pressure that I have to add into my calculation. Now notice here, they switched it around a little bit. Here there was the pressure of the gas was pushing it down. Over here, it must be a fairly low pressure because actually the column is higher on my left side. That's okay. Just orient yourself and say, hey, in some divided side, left versus right, like right at the bottom of the tube, what are the two pressures that are pressing on it? The left side and the right side, and they have to be equal. So in this figure, I've got the pressure of the gas and the pressure due to this mercury column. Pressure of the gas plus the H rho G equals, on this side, the only thing that's pressing down here, because it's open, is the atmospheric pressure. So that would equal the pressure of the atmosphere. All right, then I can just solve for, as usual, the height of the mercury or whatever you're doing here. I can measure the pressure of the atmosphere, and I can solve for the pressure of the gas. All right, so an open-ended one, not quite as easy, simply because you've got to include the idea of the pressure of the atmosphere. Here's another one here where they're showing the same kind of a thing, open-ended atmosphere, but this time they have the height on the right side a little higher. That's okay. Just take your imaginary line and say, again, left half to equals right. So on the left side, I've got the pressure of the gas. That's it. On the right side, I've got the atmospheric pressure and the height of that little column. That's a little height in this case. So the pressure of the atmosphere plus the pressure of the height of that column would equal the pressure of the gas. So either way, they just left equals right, and you can do that. All right, let's try it. 9.3. Okay. The pressure of a sample of gas is measured with a closed-end manometer. Makes it a little easier, right? As shown to the right, as shown down here. Okay. The liquid is mercury. What's the pressure of the gas? And they want it in torr and pascals and bar. All right, and there it is. So I copied that figure here. They have a gas, it's a closed-end manometer, and you can see here it's pushing that up 26.4 centimeters. So the only thing on the left side here that's pushing down is the pressure of the gas. On the right side, so pressure of the gas. Why am I writing it there? Let's just go down here. Pressure of the gas. On the right side, 26.4 centimeters of mercury. Right? That's a unit of pressure that's pushing down, and it's closed-ended, so there's no atmosphere or anything. So this is pretty simple. Like I already boxed it here, the pressure of the gas is 26.4 centimeters. Of course, we don't usually use centimeters, we use millimeters, so I can convert that, just multiply by 10, right? And so that's 264 millimeters of mercury, and there's my answer. I can take that and convert it now to bars or atmospheres or pascals or whatever else they might want. I'm not going to do that part of the problem. So just the height of the column, that was pretty easy. Let's try the next one here, 9.4. As a 9.4, they said, what's the pressure of a sample of gas measured at sea level? 1 atmosphere of pressure is atmosphere at sea level, right? With an open-ended mercury manometer as shown. So here we go. The gas is giving us some pressure. We've got the height of the mercury column and the pressure of the atmosphere. Right? But again, the left side has to equal the right side, and so we can do that. The pressure of the gas on the left equals, on the right side I've got the column of mercury and I've got the atmospheric pressure. And now I just need to solve that. Alright, well, the pressure of the atmosphere, I know that's 760 millimeters of mercury. That's the conversion, that's how it's defined. The pressure of this mercury, 13.7 centimeters. Well, that's the same as 137 millimeters of mercury. There we go. They're in the same units now. They're both millimeters of mercury, so I can go ahead and add that together. 798. There we go. 897 millimeters of mercury.